2017's paper. Okay, question number 3. 3A, the question is on the formation of pot family matrix. Let me read the question. The coding system for Variance system has 4 digits, value range for each digit from 0 to 4. The 6 parts with their code shown in this table. All right. Showing this table belong to a pot family. It is also known that pot 1, this part 2402 and also 2003 do not belong to this pot family. And pot 3 with a code of 1J21 is a member of the family. The other information given is I is less than J. So you need to obtain J, Ij, and then the pot family matrix. So among the 6 codes belonging to the forming the pot family, we still have 2 variables, unknowns, I, J. So we need to make use of this information given the clues and to find I and J. Go through. Let's start with this 1J21 is a member of it. So basically, at every digit, we must be able to find the existence 1J21 among the 6 codes here. 1J21. There's no 1 here, right? For the first digit, there's only I and also 2. So if this one is a member, so I must be 1, right? Okay. So from this we get I is 1. Any more than that? J is here. Second one. Third one 2 is here, and last one is 1. So the remaining 3 just redundant. Okay. So I equals to 1. Now we need to find J. So I equals I less than J. So J should be 2, 3, 4. Okay, among 3 possibilities. Okay, and 2402 is not a member here. 2402. Let's check for every digit. 2 is there. O number 3, O is there, and number 4, 2 is here. So we have to make sure that for the second digit, there's no 4 here. So for second digit J, we have a J here. There's no 4, so J not equals to 4, right? It can't be 4. Similarly, for this 203, 200 exists in the first code. So 3 must not appear in the last digit. 3, none of them here, but we have J, so J not equals to 3, right? So J not equals to 4, J not equals to 3, and that's the result. So J must be 2, right? So the solution. Okay, let me make this clear. You don't need to copy the solution. Okay, later you can come up to take a photo. I have 1 or 2 pages of the reference solution here. You just follow me. So basically, you got I and J, and then for the matrix, 4 digits, value from 0 to 5. So the dimension is 5 by 4. Okay, that's the matrix. And then basically the entries, you just base on all the 6 members. Indicate that. So that's 3A. Okay, 3B. Given a PFA matrix, this one concerns the PFA procedure. given PFE matrix, is it possible to quickly identify the parts that do not belong to any part families? We don't have the part family yet, right? You start with the family matrix, and we know that we normally need to apply those numerical methods like rank order, cluster, these kind of methods to convert them into a certain state. Then we can identify the part family manually. So initially there's no such thing, but is it possible to identify some parts? We know that these parts do not belong to any part family eventually. Okay? Is it possible? And give a simple example to support your answer and provide suggestion how to deal with this kind of problem in PFA analysis. Okay? I remember I did mention during lecture, if we have cases like this, right? This is a PFA matrix. Oops. All right. And each column represents a part, right? Component. And each row represents a OP code. So based on the process plan of any given part, and we can indicate the positive answers, if the plane contains those OP codes. And the problematic part is something like this. If we have a part like this in this way, if we identify a part containing most of the OP codes, we basically call this kind of problem like an iron bar, And whatever we do, because eventually the OP codes will be distributed into the established part family. And apparently for this kind of part, it won't belong to any particular part family. So this kind of part actually gives us a problem actually. So the answer is yes. Okay. Even at the very beginning, even we don't have any part family established, we know, we can identify these problems very easily. So the answer is yes. So you need to give an example like this. Okay. And we do have the example in our notes, right, in the slices. You can identify that. Okay. And how to solve it? Okay. To solve this, basically, whatever a numerical method you're going to apply, at the very beginning, you can simply remove this, because this will cause problems. Sometimes even you can't close the loop, which means it's a dead loop when you apply those iterative numerical methods. So basically, you simply remove this from the PFE matrix, and then start with. So this is the answer, okay? And that's for B, 3B. Okay, 3C. 3C refers to additive manufacturing. So we have two thin layers. The external diameter of this A and B are the same diameter. And inside here we have a square hollow. We have a triangular hollow. Inside B we have a circular hollow, the 0.8D. Okay, 0.8D diameter. And okay, and the question. There are two sub-questions. The first one is, if SLA is used for the fabrication of these two layers, and the fabrication times are equal, we know that fabrication determine the relationship between X and D. X is the side length of this triangle. Is the side of the square. Okay, the triangle, the dimension is given. So basically, for sub-question A, fabrication term SLA is used. Fabrication term equal. That's why the hatched area of this and hatched area of this should be equal. And from there, you find the relationship between X and D. Okay. And the relationship is eventually, okay, you should know it. For the same size, okay, equilateral triangle, the area, the equation is this. I did find some student couldn't memorize, couldn't remember this equation. Okay. It's a square 3 over 4, and the size square, actually, the size square, but equivalent to this. Okay, and this is for the area for the square, and eventually you equate this to, you find the relationship x equals 0.628d. Some may ask question that how many decimals you need to leave. Now, I know every one of you has a computer, has a calculator. So, but basically, if you leave it up to 2 decimals should be enough. Okay, you don't need to leave many. So that is for question A. Question B is if LOM is used for the fabrication of these 2 layers and the fabrication time also equal, determine the relationship between X and D. And this way is, calculation-wise, is even easier. LOM, the fabrication time, basically proportional to the traveling distance of the laser. Okay, basically is the summation of all the boundaries, the length of the boundaries external and internally. So for this one, for LOM, is this periphery of this, and 3 sides, 4 sides, this summation equals to, outside you don't need to, because outside the length is exactly the same. And then this one, this actually the periphery of this circle equals to this plus this. Okay. And the result is 0.2533 dx equals to. Okay, that's question 3. Let's move on to question 4. All right, a fader selected device serves an automated assembly machine on the track. And there are 2 high-level sensors and 2 low-level sensors and 1. The ideal cycle time of the machine, TC, is set at 5 seconds, TC. And the time taken for the pulse to go from N2 to N1 is 1 minute. When both sensors are off, the time taken to empty the full track capacity is 1.5 minutes, obtain N1 and N2. Okay, we are given 2 clues. The time taken from N2 to N1 is 1 minute. Right? So you can establish one equation here. Okay. This one, the second clue, when both sensors are off, the time taken to empty the full track capacity is 1.5 minutes. In this case, the track capacity actually is N2. Okay, always corresponds to the high-level sensor. Okay, N2. To empty it, it's the number of parts to be taken out is not now is purely M2, okay? Because to empty it, the bottom is 0, okay? So we should be able to establish two equations. Okay, so TC 5 seconds, RC, we use the unit number of parts per minute, so I use 60 seconds divided by 5, 12 parts per minute, and that's RC. And so from N2 to N1, 1 minute, you got this, the one equation. And then second equation, N2 divided by RC 1.5, and you calculate, you got this too. 4B. Okay, 4B is about a multi-station machine, a synchronous assembly machine, has 8 stations. The part defect rate Q is the same for each station, and the probability that defect part will cause jam is also same for each station. When Q is 0.03, it's observed that among 1,000 assembly produce 114 or with defects. At the same time, the cost of the acceptable assembly is $20 per unit. Okay. So that's under the situation that Q equals to 0.03, M is not given. Actually, from here, you should be able to find 1,000 assembly produced 114 with defect, which means 886 are good ones. So 0.886 is the UPP. From that, I believe you can find M, okay, because Q is already there. So which means you should be able to find M here. Okay, now the question asks, if CPC, if the cost per assembly need to be reduced to 19 per unit, while keeping the average production rate of the assembly unchanged. So basically, you don't want the assembly production rate affected. So you need to determine the new value of M and Q. So the currently is 0.03 and also the one you're going to calculate. But here, if you want to reduce that, you need to find the new value of M and Q. But this is the condition. Assumption given here, the cost of disposal totally ignored. So in the equation for cost per piece, this on top, CT is actually 0. Okay? And the following parameters are not affected by change in Q and M. Cost per unit per pass in all stations. And the ideal cycle time of the machine, TC, and average downtime TD. Cost per minute to operate the line, CL. So all this is not affected by if you change Q and M. So you need to find the new Q and M. Okay, let's leave it the second part. Okay, the clue is here. As I mentioned, from here you can calculate the current value of M, all right? Because you know the U is 0.886, okay? And for this part, you need to make use of this condition given, keeping the average production rate of assembly unchanged, which means RP unchanged. RP unchanged, which means TP unchanged. And TP has a general equation. Right? That's the general equation. So before and after, if TP unchanged, and TC unchanged, let's remove this. And also this one equals to number of stations, everything unchanged. So what we have is, we have this equation, MIQI equals to, that is the current one, MIQI, I use pro. Okay. You will have this relationship, okay? You have this relationship. So that is the second one. And plus, you need to make use of this, okay, and CP. CPC, that equation equals to PEP. And on top, we have a CM and plus CL times TP plus CT. And that's the general equation, yeah? But if you look at, in this question, before and after, CM unchanged, right? Material cost unchanged. TP remained the same, CL unchanged, so this portion the same, CT 0. So the denominator side actually unchanged. The only thing changed, we have 20 PEP. I use delta on top. That's the current situation, yeah? That's equation 1. And after that is, we want to reduce to 19 equals to delta, still the same, and PAP prop, right? Okay? So we know the current PAP, right? So we know the expression of this, the value of this delta. So we know this, we can calculate the PAP prop here. And PAP prop has this, PAP has this 1 minus QI plus MI QI. N is 8 station, right? So eventually you will use this equation. This equation will help us to obtain this very quickly. Because MIQI, we know the value already, right? MI times QI remains unchanged. So we can obtain QI from this. Once we have that, MIQI, we know the value, so we can obtain MI prime. Okay? So eventually, the solving procedure is actually quite straightforward. Show you the results. This is the result. So Q1 equals 0.03, PP1 equals this, power of 8, equals to 0.86. From that, you can find, you don't need to go for M1. You just obtain M1 Q1, 0.0015. So this one unchanged. And so we have M2 Q2 also equals this. And PP2 equals this PP1. All right. And then we go for PP2. The value is this. And on the left side of the issue, 1 minus Q2, actually, Q prime, actually, MIQI is still 0.005. You got Q2. And from that, from Q2, then you can get M2. These are results. Okay, from the result, actually, that remind me, I saw one student previously from that year, whose calculation skill may not be that good. But what he got is, he got the relationship correct. Somehow he got this part is wrong. And the thing is, he got M2 equal to something, 1 point something. But he caps that result. and you should immediately know that this is not right. You won't be able to get M2 beyond 0 to 1, right? If you get a Q2, beyond 0 to 1, then you know something is not right, okay? Okay, second part of the question. In practice, the assumption here we know that do not hold. Briefly discuss the impacts of the change in M and Q on CPC. This one, the answer is actually related to part one, this, okay? When you change M and Q, let's look at the assumptions. The cost is totally ignored. This one is fine. This one is the same, actually, for the situation before and after. So this one you don't need to discuss. The other thing is the parameters are not affected by change Q and M. Okay, the first thing is cost per unit. Cost per unit, that's not true. In practice, if you change Q, normally the price will change. Okay, so that you should say the change of Q would affect this. Okay, the ideal cycle time of the machine. Okay, this one is fine. Average downtime, fine. Cost per minute to operate the line. If you change M, which means the control measures, actually you have to make changes, and that also affects this. And so these actually definitely will affect finally the cost. So you just need to discuss these few items. That would do. Okay. That's for B. Final one for C. Single station machine. Oh, sorry. This one actually involves both multi-station and single station. This one, a multi-station is 4 stations to assemble 4 different components to a part. Defect rates Q, A, B, C, D are the same. Okay, there are 4 components A, B, C, D. The probability of defect part will cost Gm for each of the 4 stations is this. This is M, which means the other side, unknown. Okay, referring to this multi-station machine. The ideal cycle time M, a multi-station machine, is T seconds. On the other hand, a single station also designed to assemble the same product performs 5 work elements. And this is what happened to the 5 work element description for the single station to assemble the same product. So you can see that the element times are given. First of all, involving addition of components. The last one is fastening. All the element times T. M also XS, XS, I know. And it's known that average downtime per gem is 40 T for both stations, seconds. Okay, for multi-station and single station, TD, 40 T. The material handling time of S, single station, is 3 T seconds. That's TH. TH for single station is 3 T seconds. So when XM, XS equals 0.5, it's observed that the average production rate of batch assembly of M is 3 times of S determining Q. Okay, so basically there's only one clue. You need to find the expression of average production rate of batch assembly for M and also for S, and find this. Use this relationship 3 times, and you should be able to find this Q. Okay. And let me establish. Okay, the first part is we know that Q are the same components, A, B, C, D for both machines. And M, in this case, are the same, 0.5 for multi-station and single station. So we will have this relationship, right? The yield of product for both multi-station and single station are the same. Okay? You can establish the equation of Q is power of 4, 1 minus Q plus MQ, and then a bracket. So these are the same. And at the same time, we know that the production rate of, okay, PAP the same, so PQP, the proportion of bed assembly also the same, right? And we know that the time to produce one bed assembly for multi-station is the production rate for bed assembly for multi-station is 3 times that, meaning that the time to produce a bed assembly for single station is 3 times this. Okay, and we can find that from that, because these two are the same, so we find TPS equals 3 times TPM. Okay. So, and then from there, we find the expression TPS and TPM. So TPM equals to what? The TC is T, seconds, plus 4 station. TD is 40T, and then XM. Here, actually, the XM should be 0.5. Anyway, we leave it here. We have a Q here. And for TPS is T for single station machine. The TC cycle time is 5T plus TH another 3T, so 8T. That's the TC for single station, and then plus 4 times 4 elements involving addition of components times 40T, that's TD, and XS and Q. And then we substitute this into that relationship, right? And all the terms involve all the terms have T, so you can remove it. Okay, you can remove it. You find that substitute these two into that, and you will find eventually that is Q. Okay, you will find Q. So without obtaining the value of T, you can find Q. That's the first part of the question. And second part is compare with the setting in this, only XM and XS are changed. Okay. Changed to what value we don't know, but we know that eventually XS equals to 0.5 XM. It is observed that the yield of good assembly of M is 1.0 to 6 times than S, determining the number of S required in order to achieve the same delivery rate of good assembly of 100 M. So in this case, actually, XS, XM changed, but the whole relationship in this. Okay. The basic thinking is to obtain XS and XM first. And from that, you get the production rate for good assembly for both machines. And then you can find this relationship. So the result we use is this. This is PAP-M, okay, multi-station machine U. This is PAP-S, okay. As for Q, is still the same for both. So Q, we will use this, okay. And now we have, for single station, we have M equals to X. for multi-station is 2x. Okay, we substitute this into this, and we have this relationship. Okay, we can find the x, I believe. Okay. So eventually you will get the value of x 0.2. So for multi-station machine it should be 0.4. And finally, we find the production rate for good assemblies for both stations. And we substitute back into TPM, average production time for the multi-station machine, using the standard equation. But this time we use a different M. The value is y is for multi-station 0.4, single station 0.2, standard equation. Y is what? We've got 3t, 9t. Okay. We already know the relationship between the Ute, multi-station, single station. These are given already. So eventually we would find. So this is a general equation for TEP. Yeah? The time to produce one good assembly equals to the TP divided by P in both cases, and then you find the ratio. Eventually, you want to find the delivery rate of a good assembly in one multi-station machine equals to how many single-station machines, and that's the result. Y equals close to 3.078. One multi-station machine, the delivery rate of a good assembly equal to these 3 plus single stations. So 100 M equals to this. In this time, it's not 307.8. You should go for round it up. Okay, so that's question 17. Okay. Now let's quickly move to last year's paper. Yeah, last year's paper, the answer is only one page. Okay. Sorry, 2 pages. That's right. So, last year there was the first one. This is a coding task for you to handle, and you can certainly follow by referring to the OPEAT system, okay, which is available because it's open book. So you have that in your notes. Use that to code this digit, and I wouldn't repeat. Rotation part. Step to both end diameter externally. Internally, there's a simple hole, and there is a radial hole not on a pitch circle diameter. So the result is 14103. 14103. Second one. The coding system for, again, is regarding parts family matrix, and has 4-digit value ranging from 0 to 5, 6 parts. The code belonging to a form of part family, X, Y, and O. Part 1 and part 2 do not belong to this family, and moreover, Y equals to X plus 3, obtain X, Y. This one somehow, okay, in a similar fashion as the year before. Okay, so you need to exclude the value, possible value for x, y from this and this, and eventually by making use of this relationship to find these two values. Okay. So 25y2 is not this not belong to this. So 2, 5. Oh, first 2 is there. The last one, 2, also there. So y in the middle cannot be 0, cannot be 2, cannot be 2, cannot be 0, cannot be 4. Okay? So cannot be 4, cannot be 2, cannot be 0. So that's what you got. That's for y. Okay? And y certainly cannot be 1. Okay? And because of that, y definitely more than 3. Okay? No less than 3. Okay? And the other one is 203, also not part of this family. 203, and you got 20 here already. So the last one, there's only one variable y here. So y definitely not 3. So y, there's only one possibility. Y is 5. Right? Y is 5. Y is 5, x is 2. And these are the results. Okay. So eventually, the value range from 0 to 5, so you got 6 rows. Okay? 6 rows this time now, 4 columns. Find that. This one is in a similar way. Again, these two. These two, a single layer, okay, with the same thickness and the external diameter the same. Dimension this portion given. The only portion not given is triangle. The sides, length sides. Okay. And there are two relationships. Again, both if SLA is used for the fabrication 2 layers TA and equals to 1.3 times TB. So that actually equivalent to the relationship of the areas between A and B as well, because fabrication time directly related, proportional to the area. So you establish this and you can find x. For LOM is the traveling distance of the laser. Okay, so it's the external boundary, internal boundary summation. We have this relationship. I'll show you the results. The first one for A is for part 1 is x equals to 0.2197. And for the second part is x equals to 0.1 d. Okay. You simply need to establish the relationship. One is regarding 2 areas, the other is 2 traveling distances. Okay, so now we move to question 4. A part fader selector serves automated assembly mission on the big track. High level sensor at N2, low level at N1. The ideal cycle time of the machine is 6 seconds, TC. When the probability of the component fed by the fader will pass the selector is theta. Theta is not given. So if it's theta, then the time taken for the pass to go from N1 to N2 is T minutes. So one equation can be established here. When the probability component fed by the feeder is increased, is to 1.5 theta, the selector passing rate. is probability increase from theta to 1.5 theta. The time taken for the parts to go from n1 to n2 becomes 0.5 t minutes. Estimate the minimum parts failure rate, feeding rate f. Okay, so we have we can establish two equations: one based on this, one based on this. When theta becomes 1.5 theta. This portion there's no problem at all. So what you got? We got this. We got this delta means n2 minus n1. Okay. So just simplify the expression that when it's theta then equals t. When it's 1.5 theta is equals to 0.5 t. And RC here is given TC 6 seconds, so RC is 10 parts per minute, so we have the value. Well, inside here, okay, so inside here, that's what we got. We still have, we have a variable T1, 2, we have three variables, two equations. So apparently we can't find the exact value of f, but we can establish a relationship between f and theta. Okay. So from there, you find that f theta equals to 20. Okay. And theta equals 20, of course, over f. We need to estimate the minimum f. And theta equals this because theta should be less than 1, right? Definitely less than 1. Okay. And from that, you find f no less than 20 parts per minute. But that's not good enough. Theta actually, the range should be further narrowed. We have a theta, we have second scenario, we have 1.5 theta. So 1.5 theta also less than 1, correct? So you first move on. So 1.5 theta also less than 1. Okay? And you substitute this into this. You find that f should be no less than 30. Okay? So eventually this is the value taken. Okay? This is the value taken. 30. Okay, that's for 4b. For the asynchronous assembly machine has 6 stations, and the part defect rate is the same for each station. Probability n also the same for each station. The ideal cycle time of the machine is 6 seconds. Q, when Q equals this, M equals 0.5, the cost of the assembly, acceptable assembly CPC is $10 per unit. And sub-question part 1, when Q equals to this and M equals to this, so change from this to this. Determine the new CPC. Okay? And then, of course, the assumptions is TC unchanged, cost per unit for the parts for all stations unchanged, average down TD not changed, and CL not changed. Okay. So you need to find that. Okay. And okay, you can follow this one. You can follow that the general equation of CPC. Okay, to find to have the expression this, and from there by changing Q and M, so you recalculate PEP, okay, and then you can determine the new CPC. That there is a coincidence here, which is CL is not changed, but CL is not given, right? And here that there is a coincidence. To solve this is you notice that Q and M 0.02, 0.5, the result is 0.01, and this one also Q times M 0.01. So M times Q the same. M times the Q the same, which means that average production time per assembly TP the same, because TCN changed. So from there, actually, you can solve this part, this question quite easily. So at the very beginning is you find that M1 Q1 is 0.01. You find that M2 Q2 also 0.01. So these two the same, and that's why we have TP1 equals to TP2. Okay. So inside that, this is the general equation for CPC, and CM plus CL times CT. Tooling cost 0. So apparently on top, the top part, denominator unchanged. I use this. But using good assembly will change. Okay. So only this portion. And we find that you can calculate PEP1, PEP2. Okay. Because MQ for both situations are given. So these are the results. And finally, CPC2 equals to, this is CPC1 times PP1 divided by PP2, that equals to eventually $11.3 per unit. So that is the first part. Okay, and the second part of the question, when Q equals to 0.02 and M equals to 0.5, that was the initial situation. It's known that the cost of the base part is $3, and the cost per unit for parts at every station is $1, and TD equals to 20 TC octane CL. So this one is simply apply the general equation. Because CL is given, you need to calculate TD. So what you got is TP1. In the first situation, you substitute 6 station Q. Q times M is 0.01. That's 20 T. 20 T. 20 TC. This is TC 0.1. That equals 0.22. That's TP1. Okay. And so eventually CL, we use that general equation to find the. So CL equals to CPC times VP minus CM divided by TP, right? So that is the expression. That is CL. Eventually, you can simply do a simple calculation. Okay, so that's 4B, and last one, 4C. This one also shows the relationship between multi-station and single station when they are used designed to assemble the same product. Okay, and so description of the 4 stations, multi-station, to assemble 4 components. A single station also has the same. QM for each station are the same. TC for M is T seconds, and for a single station, the description are here, all given. Material handling time, TH, for single station 1.5 T seconds. Average downtime per gen 50 T for both stations, and that is for a single station. You can see element times 1, 2, 3, 4. These 4 involving addition components. This one is not. So the question is, when XM and XS equals 0.5, it's observed the average delivery rate good assembly of M is 5 times S, determining Q. This means the delivery rate of a good assembly for multi-station is 5 times that of single stations, meaning that the production time per good assembly for single station is 5 times that of multi-station. Okay, so you need to find the expression of the average production time per good assembly for both cases and establish this equation. Right. Okay, so
I played football twice this week, and then I played badminton with you.
We'll see. To find the production time per good assembly, we first will find the production per assembly. So TPM equals to, this is the original equation, TC plus 4 stations, Q, XM, TV. Substitute, you got this result. And for single station, you need to sum up the T 1.5, 1.5, 3, 4, 5, 5.5, then plus 1.5. 70 is the TC for single station. So you got 70. And plus, again, 4 elements involving addition of components, Q, XS, and then TD. So that equals this. So we find the expression of TP and TP multi-station, TP single station. Now, combining with the PEP. Okay, in this case, we have this relationship. Because XM equals to, because M for single station, M for multi-station, all the same. Q the same components, Q certainly the same, so that's why we got PEPM equals to PEPS. Okay. We don't need to do any calculation. Okay. And meaning that, what we have is TPS equals to 5 times TPS. Because the time to produce a good assembly equals to TP divided by P. So PEP, the denominator is actually removed from both sides. Okay? And we have this relationship. From that, certainly you can obtain Q equals to 0.005. That's the de facto rate. Second part of the question, compare with this setting with this setting. So the setting of this is changed. Only XM and XS are changed, and then XM equals 0.4, XS is unknown. It's observed that average production rate, now referring to all assemblies, of m equals to, is 5.5 times s, determining xs. The difference between this and this is the relationship here is the relationship between the average production rate equivalent to the relationship between the average production time per assembly between these two stations is the average production time per assembly for S is 5.5 times of M. So again, you need to establish this relationship to recalculate TPM and TPS. TPS equals to 5.5 times TPM. Okay. By using the new so-called the new new M values for multi-station and single station. This one is unknown. So once you have this relationship, then you can you solve to obtain XS, so or MS equals to 0.7. Okay. So these two part one and part two question actually you have to be clear about when you read delivery rate of a good assembly, which formula you apply, and delivery rate or production rate of all assembly, what formula you need to apply. So you need to be clear about this. And then with that, you can solve solve questions quite easily. Okay? Okay, so I know that this is regarding the last year's paper. I know that there are many more years exam papers available in the library. If during the revision time, if you try by yourself, you can contact me if you want to see the results. And I appreciate your understanding that we are not allowed to upload those so-called standard answers to the IBLE. But if you approach me, then I can show you. Okay, I can show you some of the results. But not all the years, not all the years down to early 2000. I don't have that. Okay, you don't have to do that many. Okay, now you can do a self-assessment before the exam, which means if you, for example, you try 4 or 5 years exam questions, you feel that you are comfortable, you roughly know the procedure to solve the questions. Okay, I think you should be okay.
4 or 5 years.
But of course the questions and the format has been changing all the time because it's open book. Okay? It's been changed over the years. Both my part, Prof. Lee's part as well. So the key is still understanding. Okay? That's a very important part. And for future consultation, that's my. My office, eh? Okay. Okay. My office at the old building, E2 0220 28. Okay. Drop me an email to that, and then we can make an appointment. Correct. And next Thursday, as I mentioned, industrial lecture. Okay. Industrial application lecture. We have a speaker invited from Syntec Institute. So I hope you try to make it. And the department requires us to require you to assign attendance as well. The talk will last about less than an hour. Okay. Okay, and well, that. that's the end of the lecture plus tutorial. And as I mentioned, you can certainly make appointment for consultation during